Now we are going to move forward to conditional distributions of continuous random variables. Now let me define the conditional distribution concept for a continuous case. Now for continuous random variables, the conditional distribution is going to be a conditional probability density function this time. Okay, conditional probability density function. So what does that mean? We have two continuous random variables, x and y is observed to be equal to y. Now, you know, in probabilistic terms, we say that the probability of y being equal to y or a specific value is 0. However, we are not saying that it is impossible. Okay, a continuous random variable is possibly taking any value within its domain. Okay, any value within its domain. But equations, they have 0 probability. But they have a density. The equations, they have a density. They do not have a probability, but they have a density. Okay? So we observe that y is equal to y. For example, imagine the automobile example. We observe here, the amount of kilometers that it has made is 15,000. So what is the conditional probability of the price of it to be less than 60,000 Turkish liras? Now, both x and y here are continuous random variables. So we can define such probability statements for continuous random variables as well. So we can observe one of these continuous random variables to be equal to a value, and we can answer the question about the other random variable. Now, in order to do that, we need to define this conditional probability density function, and that conditional probability density function is going to be denoted as f again, and in the subscript you are going to see again x given y, which means that this density function belongs to random variable x. However, it is conditioned on the observation of the random variable y, and the variable of that function is x. So we are going to develop the density function for arbitrary real values of x. And we know that the random variable y is taking the value of y. My friends, would you please allow me for 5 seconds? There is a lot of voice coming from the corridor, so I need to close my door. Please give me 5 seconds. Okay, thank you for waiting. Now, this is the conditional representation of a conditional probability density function. And how do we compute that conditional probability density function? Actually, it is very, very, very easy. Very easy. How? You divide the joint probability density function to the marginal probability density function of y at y. Okay? So if you observe that y is equal to y, then divide the joint probability density function to the marginal density value of y at y, if y is given, okay? So you are basically plugging in the values of y everywhere, and that function, that ratio function for the given value of y here is just going to be a function of x, okay? It's not going to be a function of y because y is given. You are just going to plug in that value, that specific value there. Now, of course, just like in the discrete counterpart of this example, I mean, it is very similar to the discrete counterpart, right? So in the discrete counterpart, we were doing what? We were dividing. So we were dividing the joint probability mass function to the marginal probability mass function. And here, we are dividing the joint probability density function to the marginal probability density function of the random variable that is given, that we have observation on. And of course, here, the condition is what? The condition is, a necessary condition is, the density value of the observed random variable should be positive. Otherwise, this ratio would be indefinite. And if the density is positive, then it is also possible that this random variable can take that value, right? If the density is positive, We do not say that it has a positive probability to be equal to that value, but it is possible. Okay. So actually, continuous random variables are very interesting random variables. Okay, unlikely to discrete one. I mean, discretes are always easily understood, but in the continuous case, unfortunately, the students cannot think about the density concept. Okay, density is just a measure. Density is just a measure for that random variable. It is not a probability. It is just a measure of relative likeliness for this random variable to take on that value. It is not a probability, definitely. Now, we are computing the conditional probability density function of x here on the observation of y, and in that formulation, we definitely need the marginal probability density function of y. So if you are conditioning x on y, you require the marginal PDF of y. If you condition y on x, then you are going to require the marginal density function of x. Okay, be careful about this. Just like in the discrete counterpart, if you are conditioning one variable on another, that other random variable's marginal distribution should be known. Okay. Now, just like in the discrete case, we can also check how the independent statement will work on this formulation. Now, let's just say if x and y are independent. In that case, the conditional probability density function of x over y, x given y, is going to be expanded just like in this formulation exactly. But in that case, in the case where these two are independent, the joint probability density function in the numerator can be expressed as the product of the marginal probability density functions, which will help us to cancel out the marginal probability density function of y in the numerator and in the denominator. And finally, you will get the marginal PDF of x. In other words, when two random variables are independent, the conditional probability density function of x on the other random variable will be exactly the same as the marginal probability density function if these two random variables are independent. So which means, again, x does not care anything about y at all. Okay, so it does not care whether y takes any value of y or another value. It is not important. The conditional probability density function of x is always equal to the marginal probability density function of x if these two random variables are independent. Okay,